Hello everybody, welcome back to another Gregorius Maths video. Oh, whoops. Ta-da! Much better. Okay, so today we'll be doing abstract algebra. Namely, we'll be covering cyclic groups. So, what is a cyclic group? Alright, okay. A group G is cyclic if it's generated by a single element A in G. Okay? So what do we mean by this? Well, let me just ask you. Let's just ask a question. Okay? Let G be a group and X be in G. Okay? What's the smallest subgroup what's the smallest subgroup of G that contains X? And we'll say that X is not equal to the identity element. Otherwise that would just be trivial, the trivial group. Okay? Well, it has to contain X. Okay? Has to contain the identity, which has to contain the inverse. And let's say G is a group under multiplication. So to be closed under multiplication, it has to contain all of the powers of X. But then it has to contain all of the inverses of the powers of X. Okay? And we say that this group is generated. Oh my god, what am I doing? So stupid. Okay. This group is generated by X. Okay? Now, let's see what this would look like when G is a group under addition. Okay? So we have X, we have negative X, we have E, the identity. Okay, we have 2x, we have 3x, we have more x's like that, we have negative 2x, we have negative 3x, and so on and so forth. Okay? And this is still a group generated by X. Okay? And this group is cyclic because it's generated by a single element. Alright? So, in other words, oh my god. In other words, there is a surjective function f of n equal to a to the power of n for a and g. Okay? And that's the definition. Okay, so now let's look at an example. So the classic example is the integers under addition. And what do I claim? That the integers are under addition are generated by 1. Okay? Now let's look at the group generated by 1. Okay, equals, has to have the multiples of 1, 2, 3, 4, so on, so on, so on. Has to have the identity, has to have all of the inverses. So on, so on, so on. And of course we can see that this is isomorphic to the integers. Basically a fancy way of saying the same thing as the integers, equal to the integers. Okay? So my claim was proven. Okay? But that's an infinite cyclic group. Are there finite cyclic groups? Yes, there are. The integers mod n are also a cyclic. Okay? Okay? So, why is that? Well, the reason is, again, if we look at the multiples of 1, we have 1, 2, 3, 4, 5, 6, so on, so on, till n. Then we have n plus 1, n plus 2, so on, so on, all the way up to 2n, and we can keep going. And the same for the negatives, okay? We have negative 2, 3, 4, 5, 6, all the way up to negative n. And then we have negative n minus 1, and so on, so on, so on. Okay? So it's still generated by 1. Okay, so 0 is congruent to n, mod n. 1 is congruent to n plus 1, mod n. Can carry on doing this up until n minus 1 is congruent to n plus n minus 1 mod n. Okay, and we can do this for the negatives. Negative 1 is congruent to negative n plus 1 mod n, and so on, so on, so on, so on. Okay? So now we've seen the... Alright, let's do a quick recap. We have seen let's just say, for our convenience, 2 different sub not subgroups, cyclic okay, cyclic groups. Again, the integers under addition and the integers mod n under addition. Okay? Are there any more? Nope. There are no more. That's all of them. Okay? So the only cyclic groups there are the integers mod 2, the integers mod 3, the integers mod 4, blah, blah, blah. And those are all of the cyclic groups. Okay? So now let's just prove a proposition. Okay? So first of all, yes. for the cyclic groups, don't forget the trivial group E. Just the identity element, okay? That's also quite important. Don't forget that. Okay, so let's prove this. If G is a cyclic group, then the subgroups of G are cyclic, and if F is a homomorphism, okay, of G, then the image of F is a cyclic group. Okay? So kind of two different things here. Let's look. Why? Okay. Anyway, first of all, if G is a cyclic group, the subgroups of G are cyclic. Well, we just showed that the integers, well, we didn't show that the integers and the integers mod n are the only cyclic groups, but because we know that, well, the integers mod n are the subgroups of the integers. So, and they're all cyclic. We just showed that they're all cyclic. So clearly, the first part is true. Now let's look at the second part. So, F is a homomorphism. F takes us from G to G prime, okay? So what the claim is saying is that the image of F is also a cyclic group, okay? So the image is just the range. It's just another way of saying the range. Okay? So how do we prove this? Second part. If F is a homomorphism of G, then the image of F is a cyclic group. Okay? Well, okay, if G is a cyclic group, then there is, oh my god, I can't write that. I have to do this. A surjective function okay, f of n equal to a sub n for a and g, okay, and clearly if a generates g, then f of a generates f of g, and f of g is just the image, okay? So we'll do our little box, okay? And until the next video, that is it. Goodbye.